All right, so chapter 3 here, we're going to talk about orbits and gravity, and this is just to give you an idea of when we talk about satellites and rockets and planets and orbits and things like that, you have an idea of what's going on a little bit. So we'll talk about the laws of motion, Newton and his theory of gravitation, how solar system objects orbit, satellites and spacecraft, and then when two objects interact, what their gravity is like. So this first part here, the laws of planetary motion. So Tycho Brahe and Johannes Kepler are sort of the main guys who contributed to this topic. Kepler is another important thing, and not a thing, he's a dude. Kepler he came up with these three laws of planetary motion which govern how the celestial bodies move. And this was a big deal, but it seems like, when you hear about someone, you think, wow, he must be really smart, and I'll never be that smart and all that kind of stuff. This guy, he spent 40 years tabulating experimental results of the stars before he was able to write down his three laws. So, if you do anything for 40 years, you're going to be pretty good at it, so don't give up. All right, Tycho Brahe, his observatory, he is a very famous guy. He observed a lot of things, and there's some supernova remnant named after him. But anyway, there's a little bit of history of him there and a history of Kepler here. Kepler's a big deal. Through his analysis, he developed a series of principles now known as Kepler's three laws, which describe the behavior of planets based on their paths through space. And look at this, the first two laws were published in 1609 in the New Astronomy. It's actually a very interesting story and worth reading about that on your own sometime, the history of Kepler. Anyway, the first two laws of planetary motion are that the planets, actually the orbits are not circular. So here's the sun, the Earth. It almost looks like a circle, but it's not quite a circle. What it is a little bit of an ellipse. Not quite a circle, a little bit more egg-shaped. Barely, but it's enough to make a difference. Kepler was trying to predict where the planets would be at any given time. That was the whole point of all this, to predict the motions, to be an actual wizard, not a pretend wizard. Like, there's a lot of pretend wizards out there, but he wanted to be a real wizard and actually be able to predict where these things were going to be. So his first rule was that if you take a cone, this is a famous geometry thing, if you take a cone, you can get all the shapes from it. You can get a circle if you cut right across it. You can get an ellipse if you cut at a diagonal. You can get a parabola if you cut up from the center, or a hyperbola if you cut out closer to the edge. And those are the different geometric shapes and lines and forms that you can get from the conic sections. So that was his first thing, was that the ellipse, planets orbit on an ellipse, okay? And the eccentricity, there it is, the eccentricity, another thing you have to get comfortable with, is basically how egg-shaped the orbit is. This would be an eccentricity of 0 is a circle, an eccentricity of 0.1 is almost a circle, 0.2 and 0.9, you get more and more elliptical as you get to more and more closer to 1, to the maximum eccentricity, which is 1. Okay, Kepler's second law deals with the speeds, and what Kepler's second law says is that planets sweep out equal area in equal time. So it may not look like it to you, but these two areas, A and B, are equal. They have the same square footage. Like when you buy an apartment, it's 400 square feet or whatever, that's the area that you can walk around in. This area, even though it's a different shape, same area. Now, what that means is that you're going from point A to point B around your orbit faster than you're going from point A to B around the orbit here. So what it says is that slower, faster, slower, faster, slower, faster, slower, and so on. And so that was one of his laws, that it's called the law of equal areas. So sweep out equal areas in equal times. The third law says that if you've got, so first law, orbits are not circles, they're ellipses. Second law, as an object orbits a body, it goes fastest when it's closest and slowest when it's further away, because it sweeps out equal areas, the area that it sweeps out here, whoosh, as it moves. is equal to the area here. Of course, this thing is going to move all the way around. We're just looking at equal times. This is the same amount of time from these 2 points. Okay, so that's first law, second law. So first law, second law. Third law is that if this is your sun, the time it takes to orbit the star if you're here is less than if you're out here. It's going to take longer for you to orbit further away. And there's a very specific relationship. The time it takes, the period, squared is proportional to the distance, a, cubed. So if your radius is a, then p squared is proportional to a cubed. That's what that means. And that's just because there's a couple numbers in there that makes it a proportionality number instead of saying equals, because it's like p squared is equal to, I can't remember now, shoot, it's like 4 pi a cubed over g m1 plus m2, something like that, the two masses. Anyway, these are all numbers and constants, but your a cubed is what comes out, so we draw a proportionality thing so we can ignore all this other stuff. Anyway, okay, so what we're saying here is that, for example, the Earth is 1 AU away from the sun, so the sun's here, Earth is here, 1 astronomical unit. It takes 365 days for the Earth to orbit the sun. So you could say p squared is proportional to a cubed. So you could say 365 days squared is proportional to 1 AU cubed. Okay, and then that equation I drew a little bit ago, it's got, I don't know if we have the actual equation written down here. No, they don't have the full equation. But it's got, you can solve for the mass of the sun and the mass of the Earth are in that equation. So this is one way, using the Earth and measuring how long it takes to go around the sun is one way to measure the mass of the sun and measure the mass of the Earth. Okay, so that's the Kepler's 3 laws. So there's your 3 laws. Make sure you know what these are and what they represent. Okay, boring. All right, I'm moving on. Yeah, anyway, continuing on. So Newton came along. Newton's pretty cool. He was obsessed with science because he hated farming. He was on a farm with his family, and he refused to do any farming. He decided to do math instead, and that's weird and unusual, but, you know, hey, he was a very good mathematician. If he was a farmer, he probably would have come up with some really cool crops. Anyway, he came up with the laws of motion. The first law says an object in motion stays in motion. An object at rest stays at rest unless acted upon by an outside force. That's a big deal because, think about it, nothing will stop the moon. There's nothing to stop the moon. The moon is orbiting around the Earth. That's it. Unless something comes along and stops it, it will continue to do that. That's a big deal. The second law says that if you're going to change the motion of something, then you need to apply a force to it. And when you apply a force to it, it will cause it to move proportional to the mass. So the first law is that principle. The second law is F equals ma. The third law is that for every action there is an equal and opposite reaction. In other words, if your mass is low in one case and big in the other case, the force might be the same, but your accelerations are going to be very different. So this is why when you punch a wall, it hurts, right? Because it's actually punching you back. And the wall, truthfully, the wall probably weighs more than you, and that's why it can exert a greater force or a greater acceleration to you. It'll stop you instead of your thumb or your wrist going through it or something. Okay, so anyway, there's some interpretation here of Newton's laws. You can read that to better understand it, but it's pretty amazing if you think about it, how he came up with that and how that leads to a whole bunch of consequences. Okay, then there's this concept here of mass, volume, and density. You can read that. It's important to understand this conceptually because the density of an object is related to its mass, and we could have something like Jupiter, which is huge, but it's also made of gas, so it's less massive than it would be if it was, you know, made out of rock and other more dense things, but, you know, so anyway, when we talk about planets and dust and gas and stuff, we need to understand density. Another important physics concept is angular momentum. There's a ice skater here, and she's got her arms out. And then as she starts to rotate, what does she do? She brings her arm in and rotates even faster. And you know this on an office chair. You spin around with your legs sticking out, bring your legs in, and you will spin up and go a lot faster. Okay, so that's, um, uh, you know, conservation of angular momentum. We have to know what this is conceptually, angular momentum and its conservation, and what that leads to, because that's how the stars and planets and everything form. So anyway, just be aware of what that is. So Newton's universal law of gravitation. Here it is. Looks scary. It's not. It's 4 numbers multiplied together. If you want to determine the force of a planet on you, G is this number. It's a constant. You need to know the mass of you and the mass of the planet and how far away you are from its center, and you can calculate the total force that the planet is exerting on you, or the moon on the Earth, or the Earth on the Sun, or the Sun on Jupiter, or whatever. That's this equation. That tells you everything. Kind of amazing. And that's Newton's universal law of gravitation. If you calculate what this is, you get that the acceleration when you fall is 9.8 meters per second squared. And that's how quickly things accelerate when you jump out of a plane or whatever. Acceleration due to Earth's gravity, etc. So orbital motion and mass. Kepler's laws describe the orbits of the objects whose motions are described in Newton's laws of motion and the law of gravity. And then knowing that gravity is the force that attracts planets toward the sun, however, allowed Newton to rethink Kepler's third law. Okay, so Kepler's third law was this p squared is proportional to a cubed, right? And anyway, let's see if we can see the full equation. And I still don't, I thought they'd put the full equation here. Anyway, okay, so basically the third law adds these, well, what Newton did was to add these masses back in, and then you can figure out what the masses of the objects are. Which is pretty cool. Okay, continuing on. So, orbits in the solar system. So, anybody here play Kerbal Space Program? If you don't, you should try after the semester's over, because it takes a lot of time to figure it out. But, anyway, in our orbit, so let's say this is the sun, and let's say Earth is coming in, goes faster, slows down, faster, slow down. We're actually closer to the sun in the winter, ironically, and we move a little bit faster around in our orbit during that time. But there's some important points in this orbit. Where you're moving fastest is when you're closest to the object, and that's called perihelion. When you're furthest away, that's called aphelion. For moon or satellite orbiting Earth, the terms are perigee and apogee. So if this is Earth, and let's say the moon, or let's say you've got a communication satellite orbiting around Earth, then this becomes perigee and apogee. And those are just the terms for the satellites and their orbits. Okay, Mercury has the shortest orbit because it's the closest, and it's so because of that p squared is a cubed, it should have the shortest period. These are some solar system orbits here. You can see the Mercury, Venus, Earth, Mars, Jupiter. Okay, those are all circular almost. They're very close to, there's the eccentricity of Venus's orbit is 0.01, 0.02 for Earth. So the orbits are barely elliptical, but they are not circular. That's an important point for predicting their orbits. And then you've got a bunch of other stuff here. Ceres and Vesta are dwarf planets or giant asteroids. Hygeia, Pallas. Halley is a comet here. It has a 75-year orbit around the sun, and it'll be back in like the year 2060. I have a reminder in my reminders app for that. And if iCloud's still around. And another comet here, which comes way out of space and goes into way other places. Okay, motions of satellites and spacecraft, yada, yada, yada. So how does an orbit work? Okay, the first thought experiment was Newton's cannon, and what he imagined was if you get on top of a big mountain here and you shoot a cannon forward, it's going to fall faster, 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 faster until you launch something in orbit. So that's the whole idea with launching a rocket. You launch it from Florida. The Earth rotates this way, so you've already got some speed from the Earth's rotating motion. So you launch it this way, and you try to get it to go fast enough so that you end up putting a rocket in orbit. So as it falls towards the Earth, it's moving enough over to the side that it's always outrunning the Earth. And that's the idea. You got to go fast enough to get it in orbit. These are a picture of all the satellites that we have. This is probably an incomplete picture. We have a bunch more satellites than this orbiting the sun. Okay, so to get out of Earth's gravity, it needs to reach escape velocity, and that's the speed it needs, a rocket needs to get before it can escape the gravity of Earth, or whatever planet it's leaving from. So we can easily launch out of the moon, because its gravity is so weak. It's a little bit harder to get out of Earth's gravity, but we can do it on a regular basis. All our satellites are for that. So when you have more than two objects interacting, it gets complicated. So if you want to understand the mechanics of millions and billions of stars interacting with each other, you need a supercomputer to help model that. And that's what this is a picture of, is a supercomputer facility. Blah, blah, blah. Neptune. This is pretty cool. Neptune was discovered by the orbits of the planets before it was seen. So we were looking for something that, I say we as if I was there, but the orbits didn't quite match what you'd predict, but it made sense if there was another more distant planet out there pulling on it. And lo and behold, they found it, and it became Neptune. Okay, so there's a great section here on poetry. This is good. I definitely recommend reading that. And then that's the end of the chapter. So here's your terms. Make sure you know these terms. And you can, of course, go through the summary here and then read the review questions here and just try to talk through them and think about what they're telling you. Okay, bye.